All right, today we are diving deep into one of the biggest engineering feats on the entire internet, Facebook's social graph. We're going to look at the system they built, called TAO, that manages the insane web of connections between billions of people and, well, trillions of things. This is the architecture that literally powers our social world.
So, to get our heads around this, let's just start with a wild question. Every single time you open up Facebook or just glance at your notifications, you're making a request. Now, multiply that by billions of users. How in the world does the system even begin to handle over a billion with a B, read requests every single second?
Yeah, you're seeing that right. 1 billion. That's the minimum number of reads the system has to serve up per second. It's a number that's just kind of hard to wrap your brain around, but it is the absolute core of the problem that Facebook's engineers had to solve.
Okay, so here's our game plan. First, we're going to look at just how massive this challenge really is. Then, we'll see why their first attempt at a solution completely fell apart. After that, we'll meet the star of the show, TAO, and see how it works all over the globe. Then, we'll get into the really clever trade-off that makes it all possible. And finally, we'll just look at the mind-blowing performance numbers.
All right, first things first, the billion user challenge. You know, it seems simple, but why is this so difficult? Well, when you load your Facebook feed, it isn't just one static page. It's this completely custom-built view made just for you in a fraction of a second. The system has to race to grab hundreds of different things, your friends' posts, photos, comments, likes, and for every single one of those items, it has to check, are you actually allowed to see this? It does that for everything, every time.
So in the early days, Facebook used a setup that was, pretty standard for the time. You can think of it like this. All their data lived in these big digital filing cabinets. Those are the MySQL databases. And to make things faster, they put a layer of sticky notes on top for the stuff people asked for all the time. That's memcache. It's a very common approach called a look-aside cache, and honestly, it worked great for a while.
And that brings us right to our next point, when the cache cracked. That simple, clever system that helped them grow so fast, well, it started to buckle under the pressure as Facebook just exploded in popularity. The digital sticky notes just weren't enough anymore. They couldn't handle the complexity or the sheer volume of a worldwide social network.
Okay, this slide is super interesting because it shows us exactly where the cracks appeared. First, memcache is just a simple key-value store. It's just not good at understanding relationships, so asking who liked this photo was super inefficient. Second, a lot of the logic was on the client side, and that created this huge risk of what they call thundering herds. Just imagine a really popular post's data expires from the cache. Bam! Suddenly millions of requests would stampede right past the cache and slam into the database all at once, totally overwhelming it. And last, just making sure you could see your own new post was slow and expensive because of how data had to be copied around.
And this is where the hero of our story comes in. TAO, a graph-aware system. Instead of just slapping more band-aids on the old system, Facebook's engineers decided to build something totally new from scratch. They built a system designed to think about data the way Facebook actually works, not as a bunch of separate pieces of information, but as one gigantic, interconnected graph.
You know, the core idea behind TAO is actually brilliantly simple. It really just thinks about two things. First, you've got objects. These are the nouns in the graph. A person, a photo, a place you check in. These are the nodes. And then you have associations. These are the verbs, the connections between those objects. They're the edges. So you're not just an object, you have a friend's association with another user object. You have an authored association with a comment object. It perfectly mirrors how the real social world works. And check this out. This is where that model becomes so powerful. The questions you ask it become incredibly simple and direct. Instead of some super complicated database query, you just ask the graph a plain question. You want the 50 most recent comments? That's just an assoc range query. Want to know how many people are checked in somewhere? That's an assoc count. The code directly reflects what's happening on the screen. It's beautiful.
So, okay, the data model is genius, for sure. But how do you actually make it work for billions of people all over the planet? I mean, that is a completely different challenge, and it's where we get into TAO's actual architecture.
The whole thing is built in 3 logical layers. So down at the bottom, you still got those filing cabinets, the MySQL databases. They're sharded, which is just a fancy way of saying they're broken up into smaller, manageable chunks. But right on top of that is the leader tier. This is a really smart cache that acts as the boss. It's the only layer that ever talks to the database, and it handles all the writes. Then, at the very top, you have the follower tiers. These are just massive layers of caches that do the grunt work, handling that billion-plus read requests from all of us. And here's the key. Followers only talk to leaders. They never ever touch the database. This is what protects the database from getting crushed.
So how does this work geographically across the whole planet? The logic is really slick. When you open your feed, your request goes to a follower cache in a data center that's physically close to you. This makes reading your feed feel instantaneous. But anytime you write something, a post, a like, a comment, that request gets sent all the way to a single master region. This setup means your experience is always super fast, no matter where you are.
And now we get to the secret ingredient. The one big idea that makes all of this global speed actually possible. This is the absolute core design decision of the entire system, the consistency trade-off. See, to be this fast and this reliable, TAO deliberately chooses not to be perfectly, instantly consistent.
The original paper says it perfectly. TAO provides eventual consistency. What this means is, when you post something in the master region, TAO doesn't promise that every single cache in every data center on Earth is updated in the exact same nanosecond. What it does promise is the eventual delivery of that update. The data will get there. It will become consistent, just not instantly.
Okay, here's the best way to think about this. A bank transfer absolutely needs strong consistency, right? When you move money, you need that change to be reflected everywhere, instantly, perfectly, no room for error. But a Facebook like, that's a perfect case for eventual consistency. If your friend in Tokyo sees your like a half second after your friend in California, does it really matter? No, not at all. And in exchange for accepting that tiny potential delay, you get a system that is incredibly fast and basically never goes down. It's a brilliant trade-off.
So, the last question is the most important one. Did this massive engineering project and this really fundamental trade-off, did it actually pay off? Well, let's look at TAO by the numbers. This chart right here, wow. This justifies the entire design of the system. A staggering 99.8% of all the things happening in TAO are reads. Only a tiny fraction, 0.2%, are writes. This shows you exactly why the system is so obsessed with making reads fast, because that is overwhelmingly what we, the users, are doing all day long. We're consuming content. And here's the proof in the pudding. When the data you want is right there in that top-level follower cache, a cache hit, the average response time is just 2.4 milliseconds. I mean, that's insanely fast. And even when it misses and has to go ask a leader, it's still pretty quick. This amazing performance is a direct result of that whole multi-layered cache design we talked about.
But this number, this one right here, might be the most jaw-dropping one of them all. This is the success rate. 99.9995% of all requests made to TAO succeed. That shows a level of availability and resilience that is almost unheard of at this kind of scale. The system isn't just fast, it's unbelievably tough.
So let's end on this thought. What TAO really teaches us is that when you're building something to connect the entire planet, perfect instantaneous consistency might not actually be the right goal. Maybe the real goal is massive availability and incredible speed. And to get there, the engineers made a really smart choice. They traded a tiny bit of right now for a whole lot of always on. It kind of makes you wonder, in this world that never stops, what's the real price we pay for instant?